4 light years sounds close. It sounds safe, like our cosmic neighborhood. But what if the space nearest to us is not calm, not empty, and not stable at all? In the last 2 years, the James Webb Space Telescope has revealed planets that disappear, worlds that wander alone, black holes that grew too fast, and environments where nothing should survive. These discoveries are not happening at the edge of the universe. They are happening right next door. If you enjoy stories that change how you see reality, a like and a subscription help more than you know. Now take a breath. We begin. 4 light years. That number sounds small, almost harmless. 4 light years is the distance between us and Alpha Centauri, the nearest star system to Earth. In everyday terms, it feels close. If light itself were a vehicle, it would arrive there in the time it takes a human to finish college. In cosmic language, Alpha Centauri is our backyard. And for decades, scientists assumed that whatever happened there would be simple, stable, predictable. After all, proximity feels comforting. The closer something is, the better we think we understand it. But the universe does not work that way. In August 2024, the James Webb Space Telescope pointed its mirrors toward Alpha Centauri A, not because scientists expected surprises, but because the system was supposed to be boring enough to calibrate instruments. Instead, Webb found something that should not have been hiding there at all. A massive planet, a gas giant, roughly the mass of Saturn, orbiting Alpha Centauri A at about twice Earth's distance from the Sun. Not drifting far away in deep space, not hugging the star in a tight scorched orbit, but sitting in what astronomers call the habitable zone. This does not mean the planet itself can host life. Gas giants have no solid surface. But it does mean something else. Moons. Large gas giants often host dozens of moons. And some of those moons, if massive enough, could hold liquid water beneath thick atmospheres or icy shells. This is not science fiction. We see it in our own system. Europa, Enceladus, Titan. And suddenly, the nearest star system to Earth was no longer just a point of light in the sky. It was a place where complex worlds might exist. But then, something unsettling happened. In February 2025, astronomers tried to observe the planet again. It was gone. No signal. No glow. No shadow in the data. They searched again in April. Still nothing. The planet had vanished. At first, the idea seemed absurd. Planets do not simply disappear. Not on human timescales. Not in stable star systems. So scientists did what they always do when reality refuses to cooperate. They simulated. Millions of simulations. They tested orbital configurations, gravitational interactions, instrumental errors, background noise, and slowly a picture emerged. The planet was real, confirmed by multiple data sets, including ground-based observations going back to 2019. It had not vanished, it had moved. Unlike Earth's nearly circular orbit, this planet follows a highly elongated path, an extreme ellipse. Sometimes it swings close to its star, disappearing into the glare. Other times it drifts far enough away to become visible again. This explains the vanishing act. But it raises a deeper problem. Alpha Centauri is not a simple system. It is a binary. Two stars, Alpha Centauri A and B, locked in a gravitational dance, orbiting each other every 80 years. Their gravity stretches space, twists orbits, and destabilizes anything that lingers too long in the wrong place. According to older models, a planet in such a configuration should not survive for billions of years. It should be torn apart, or ejected, or flung into interstellar space as a rogue world. Yet this planet endured, which means our understanding of orbital stability is incomplete. And if one massive planet can survive in such chaos, then the quiet assumption that nearby systems are simple begins to collapse. This discovery also carries another implication. If confirmed, this would be the closest exoplanet ever directly imaged. Not inferred, not detected through stellar wobble. Actually seen, a real world, 4 light-years away. Close enough that future propulsion concepts, solar sails, laser-driven probes, could reach it within a century. But here is the uncomfortable truth. Closeness does not mean safety. Because Webb did not just show us a nearby planet. It showed us a nearby system that is unstable, dynamic, and hiding complexity behind familiarity. The universe does not reserve chaos for distant galaxies. It exists right next door, and Alpha Centauri is only the beginning. Because while Webb was watching a planet vanish and reappear around our nearest neighbor, something else was moving much closer. Space feels empty, vast, calm, controlled, but that feeling is an illusion created by distance. In reality, our solar system is moving through a swarm of debris. Rocks left over from planet formation, fragments from ancient collisions, objects that cross Earth's orbit quietly, invisibly. Most of the time, they miss us. But sometimes they don't. On December 27, 2024, astronomers detected something new, a small point of light drifting against the background stars. They named it 2024 YR4. At first, it did not look alarming. Objects like this are found regularly. Small near-Earth asteroids pass by all the time. But as days passed and its orbit was refined, something uncomfortable emerged. The trajectory was wrong. Early calculations showed a non-zero chance that this object could strike Earth on December 22, 2032. The probability was small. Then it grew. At its peak, the risk reached nearly 3%. To the public, 3% sounds harmless. To planetary defense scientists, it is terrifying. Because space does not offer second chances, the asteroid measured somewhere between 130 and 300 feet across, about the height of a 15-story building. Not a dinosaur killer, not a planet-ending event, but large enough to flatten a city. An impact of this size would release energy equivalent to multiple nuclear explosions. The shock wave would level everything nearby. Heat would ignite fires miles away. And this time, the warning window was short, less than 8 years. That might sound like a lot. It isn't. Deflecting an asteroid requires time, years to design a mission, years to launch, years to intercept. If the probability had climbed higher, there might not have been enough time to act. That is when NASA made a decision that surprised even experienced astronomers. They pointed the James Webb Space Telescope at the asteroid. This was extraordinary. Webb was built to study the early universe. Galaxies billions of light years away, ancient stars, the first light after the cosmic dark ages. Its time is scheduled years in advance. Every hour is precious. And yet, Webb was redirected to track a rock drifting through our neighborhood. Why? Because Webb sees something other telescopes cannot: heat. In visible light, asteroids are deceptive. Their brightness depends on two things: their size and how reflective they are. A small shiny asteroid can look exactly like a large dark one. That uncertainty is dangerous. Infrared light solves this problem. Heat does not lie. A warm object radiates energy based on its true size, regardless of surface color. By measuring the infrared glow, scientists can determine how big the object really is. Webb's observations in March 2025 delivered clarity. The asteroid was roughly 160 feet wide. Still dangerous. Still capable of regional destruction, but smaller than the worst-case scenarios. More importantly, Webb's data refined the orbit. By late February, scientists announced that the impact risk had dropped to near zero. Earth was safe, but the relief was short-lived, because the real lesson was not about this asteroid. It was about what it revealed. The object had been discovered less than 8 years before its potential impact. If its path had been slightly different, if its orbit had been more chaotic, if the warning had been measured in months instead of years, we might not have been ready. There are millions of near-Earth objects. We have cataloged only a fraction of them. Many are dark, many are small. Many approach from directions where telescopes struggled to see. Webb proved it can help. But Webb cannot watch the entire sky. Something else is out there. Something we have not found yet. And while scientists were calculating asteroid trajectories and refining probabilities, Webb turned its gaze away from danger close to home and toward a different kind of loss. Not a collision, but a disappearance. Worlds that once looked promising and then fell silent. 40 light years. In cosmic terms, that is still close. Not next door like Alpha Centauri, but close enough to matter. When astronomers announced the discovery of the TRAPPIST-1 system in 2017, the reaction was immediate. 7 planets, all roughly Earth-sized, all rocky, 3 of them sitting in what looked like the habitable zone. For the first time, humanity had not found a single promising world, but an entire system of them. It felt like abundance, like confirmation that Earth was not special. The star itself was small and dim, a red dwarf. That seemed like an advantage. Red dwarfs live longer than any other type of star, trillions of years. If life needs time, red dwarfs offer more of it than the universe has existed so far. For years, TRAPPIST-1 became a symbol of possibility. Concept art showed blue oceans, clouds, alien skies. And then James Webb looked closer. The first planet Webb examined was TRAPPIST-1b, the innermost world. Webb measured its temperature by watching the planet slip behind its star and reappear. A simple method, reliable. The result was brutal. The surface was scorched, no atmosphere. Bare rock, baking under constant radiation. Then came TRAPPIST-1c. Same story, no thick atmosphere, no protective gases, another dead world. The disappointment was manageable. These inner planets were expected to be harsh. Hope shifted outward, to TRAPPIST-1d. This planet sat right on the edge of the habitable zone. It received roughly the same amount of energy that Earth receives from the Sun. If liquid water could exist anywhere in the system, this was the place. In August 2025, Webb's data arrived. Its instruments searched for water vapor, carbon dioxide, methane, the molecules that define breathable worlds. They found nothing, no clear atmospheric signatures. The conclusion was careful. Scientists always are. But devastating. TRAPPIST-1d likely has an atmosphere as thin as Mars or clouds so thick they block detection or no atmosphere at all. The lead researcher said it plainly. We can rule this planet out as an Earth analog. Confirmed. Another candidate crossed off the list. The reason was not the planet. It was the star. Red dwarfs are deceptive. They look calm, dim, gentle, but they are violent. They unleash powerful flares, bursts of radiation far stronger than anything our sun produces. These flares strip atmospheres away molecule by molecule, and the planets orbit extremely close. A year on TRAPPIST-1b lasts only a few Earth days. Even the outer planets are trapped in the blast zone. This is the paradox of red dwarfs. They offer time, but they take protection. The inner worlds are likely sterilized. The middle ones are uncertain. Only the outer planets, TRAPPIST-1e, F, G, and H, still hold faint hope. Webb is still watching them. 15 additional observations are scheduled for TRAPPIST-1e alone. Scientists are trying to subtract the star's violent activity from the data. It is difficult. Red dwarf flares contaminate measurements. They mimic atmospheric signals. Separating planet from star is like trying to hear a whisper during a storm. Early hints suggest TRAPPIST-1e may have a nitrogen-rich atmosphere, possibly similar to Titan, but nothing is confirmed. And that uncertainty matters. Because red dwarfs make up about 70% of all stars in the Milky Way. If planets around red dwarfs cannot retain atmospheres, then most potentially habitable worlds may be lifeless. The search for life narrows, not because planets are rare, but because stability is. TRAPPIST-1 taught us something uncomfortable. Finding Earth-sized planets is not enough. Finding planets in the habitable zone is not enough. The star matters. Violence matters. Time alone does not guarantee habitability. And while astronomers were watching worlds slowly lose their air, Webb uncovered something even harder to accept. In the early universe, things were growing far too fast. Objects that should have taken billions of years were already mature. Monsters forming in the dark. The universe is 13.8 billion years old. That number is not an estimate. It is one of the most precisely measured facts in cosmology. And for decades, Scientists believed they understood how structure formed within that time. First came darkness, then the first stars, then small galaxies, and slowly, over billions of years, massive galaxies and the supermassive black holes at their centers grew together. Slowly was the key word. According to every major model, black holes should take a long time to grow. They are limited by physics. As matter falls in, it heats up. That heat produces radiation. That radiation pushes outward. This balance creates a natural speed limit called the Eddington limit. Feed too fast, and the black hole chokes on its own light. Or so we thought. When the James Webb Space Telescope began looking deep into the early universe, it expected to see seeds, small black holes. Just beginning. Instead, it found giants. In 2025, astronomers announced the discovery of a supermassive black hole inside a galaxy that existed only 570 million years after the Big Bang. The galaxy's name is technical and forgettable. What matters is the ratio. In the modern universe, black holes make up about 0.01% of their galaxy's mass. This one was closer to 10%, 1,000 times larger than expected. This was not a marginal discrepancy. It was a violation. Confirmed, peer-reviewed, published. And it was not alone. Webb found hundreds of similar objects scattered across the early cosmos. Compact, bright, red. Astronomers began calling them little red dots. At first they looked like galaxies, but their light told a different story. Their brightness did not come from stars alone. It came from hot gas spiraling into black holes at extreme speeds. Some were feeding at 40 times the Eddington limit. That should not be possible. Yet the spectra were clear. The gas was moving at millions of miles per hour. Temperatures were high enough to ionize atoms. Energy output rivaled entire galaxies. Something was wrong with the timeline. Either black holes were born much larger than we assumed, or the early universe allowed feeding rates that no longer exist today. Or our models were incomplete. This discovery forced scientists to revisit uncomfortable ideas. One possibility is direct collapse. In the early universe, gas clouds were denser, cooler, less polluted by heavy elements. Under the right conditions, a massive cloud could collapse straight into a black hole, skipping the star phase entirely. A heavy seed. Another idea involves supermassive stars, hypothetical objects hundreds of times more massive than our sun. Short-lived, unstable, they would collapse quickly, leaving behind black holes already enormous. Neither explanation is confirmed. Both have problems. But the data does not care about elegance. The black holes are there. And they are too big. What makes this more unsettling is how common these objects appear to be. The abundance of little red dots suggests this was not a rare accident. It was standard. In the first billion years, black holes may have grown first, and galaxies struggled to keep up. This flips the narrative. Instead of galaxies nurturing black holes may have shaped galaxies from the beginning. They heated gas, regulated star formation, sterilized regions. The early universe was not a gentle nursery. It was competitive, fast, unforgiving. And while Webb was revealing these ancient monsters, it uncovered something else that should not have survived that chaos. Galaxies that were too big, too bright, and too organized. Too early. Before James Webb, astronomers had expectations. Not guesses. Expectations built on decades of observation, simulation, and theory. In the first few 100 million years after the Big Bang, galaxies were supposed to be small, dim, chaotic. Collections of gas and a few young stars. Building blocks, nothing more. There simply had not been enough time for anything large to form. Gravity works slowly on cosmic scales. Gas needs time to cool. Stars need time to ignite and die, enriching their surroundings. That was the story. Then Webb looked back, and the story broke. In its earliest deep-field images, Webb detected galaxies that appeared massive, bright, and structured less than 500 million years after the Big Bang. Some of them contained tens of billions of stars. That number matters. Our own Milky Way took more than 13 billion years to reach its current size. Yet here were galaxies approaching similar mass when the universe was barely an infant. The headlines were dramatic. Universe breakers. Impossible galaxies. Models in crisis. At first, some scientists wondered if Webb was wrong. The telescope was new. Its instruments were unprecedented. Calibration errors were possible, but follow-up studies confirmed the findings. The light was real. The distances were real. The galaxies existed. So researchers searched for explanations. One possibility was misinterpretation. Brightness does not always mean mass. A galaxy powered by an actively feeding black hole can appear much larger than it truly is. And that turned out to be part of the answer. When astronomers carefully separated starlight from black hole light, many of the largest early galaxies shrank. The crisis softened, but it did not disappear. Even after accounting for black hole contamination, Webb still found about twice as many massive galaxies in the early universe as models predicted. Not impossible, but uncomfortable. Something was accelerating galaxy growth. The early universe was different. Gas was denser. Radiation fields were stronger. Cooling processes worked more efficiently. Stars may have formed faster because stellar winds were less effective at blowing gas away. In simpler terms, early galaxies were better at turning raw material into stars. Webb added another surprise in early 2025, a massive spiral galaxy nicknamed the Big Wheel. Spiral structure is not easy. It requires stability, time, order. Spiral arms form when stars settle into graceful rotating patterns over billions of years. Yet the Big Wheel existed less than 2 billion years after the Big Bang. Elegant, organized, mature. This discovery changed the tone of the conversation. The early universe was not purely chaotic. It had pockets of calm. Regions where gravity, gas, and time aligned just right. But this calm was fragile and short-lived, because when galaxies form quickly, they also burn through their fuel quickly. And when fuel runs out, galaxies die. Webb found evidence of something no one expected to see so early: a dead galaxy. A system that had already stopped forming stars when the universe was less than 700 million years old. Star formation is the heartbeat of a galaxy. When it stops, the galaxy becomes quiescent, quiet, aging, slowly fading. These galaxies are common today. They should not exist so early. The most likely cause is a black hole. When supermassive black holes feed aggressively, they do more than grow. They heat surrounding gas. They drive outflows. They shut down star formation. This process is called feedback. Webb's observations support this. The dead galaxy shows signs of past black hole activity strong enough to sterilize it. Published, confirmed. The implication is unsettling. Some galaxies live fast and die young. The early universe was not just building structures, it was destroying them. Creation and destruction were happening side by side, and that chaos had consequences, especially for planets. Because stars born in violent bursts do not offer stable environments. Disks are disrupted. Orbits are unstable. Radiation is intense. The places where complex worlds could form were rare. And yet, some worlds did form. Not around stars, but without them, wandering alone through the darkness.